So welcome to lab number 4, and may the Lord be with all y'all. This lab is called vector addition, or on the down low, it's called Lopes Migration. So every year, the Lopes, they take a little migratory path across campus. No one knows what path they're going to follow until they show up to class. But it sort of look like this when you're all done. All right, so you're going to take a little orienteering trip across campus using a compass and something for you to measure distance. And we'll give you a couple of suggestions, but you'll be working with your group to figure out just what that's going to be. But anyway, for instance, you usually start out at building 1. So you can see building 1 right here, and we're at the southeast corner of the and it says, take off in that direction, right over there, travel so far and at a particular angle. So how do we measure angles? Well, when you're a lope, you have to use a compass. And a compass is a little different than a mathematical angle because they call 0 degrees 90 degrees in our usual case. So over here we got a compass rose right here, and you can see due north is 0 degrees, or once you go all the way around, 360 degrees. Okay, and then the angles increase to the right, and that is called clockwise, whereas you know, usually in math, we put 0 degrees over here on the x-axis, and then we go counterclockwise. Well, the nice thing about all this is that you can do all your calculations, but all you have to do, but the only difference is you'll have to flip sine for cosine and cosine for sine. Because straight up is going to be like the positive x-axis, but you know it's normally your y-axis. And then over here, this would be 90 degrees from that point. And it turns out everything works out just fine. All the signs work out, everything's great. But anyway, when you go hiking, everything is measured off north because you use a compass, and the Earth happens to be a large magnet, and its south pole, its magnetic south pole, is basically aligned with the north pole of the Earth. So over here I have a compass, and by the way, when we use a compass, we use it horizontally. Okay, so if you ever get a compass out, you would orient the compass so it's nice and horizontal like that. Now, this little arrow right here should be pointing, well, this is the south end over here. North is through that wall. We're in room 331. So north is through the wall in that direction right there. And I'm telling you, it's straight that way. And look at the compass needle. It's way off to the right by about 25 degrees. Now, there's some big magnetic field in this room because I've moved this thing around the whole room, and I'm still getting this large, and they call it declination, magnetic declination. So it's off in this room by 25 degrees. But if you go outside, or you go into our physics lab across the hall, it should be over here about 11 degrees. So the Earth's magnetic field isn't quite due north in Phoenix. It points about 11 degrees off due north. So when you go to actually do the experiment, you would actually have to add 11 degrees to all your measurements, or you could just use your compass that's on your cell phone and go into the properties, the settings, and you could set it for true north. So they get that out of there. So remember, it's called magnetic declination. Okay, so let's go back up to the board over here. So due north is 0 degrees or 360, and come all the way over here. East is 90 degrees, south is 180, west 270, and then back home north 360 degrees. So you'll be getting 6 bearings, they're called. So this red line right here, it would be bearing number 1. And you get them on a piece of paper, but when you actually walk them out, you're doing vector addition. And you're doing it graphically. Okay, graphically. So you're using a compass, a protractor, and you're using something to measure distance. And when you get to this point, the next bearing comes right off the end of that one and goes to this point over here, and then down here, and here, and here. And notice all these, and this is your final point right here, and you connect the original vector to the end vector, the nose of the final vector, and that gives you your resultant vector, which is the sum of all these vectors. So up here at the top, vector addition, R is your resultant vector, and that's equal to the A vector plus the B vector plus C, and so on, as many as you have. All right. Now, hey, wait 1 second. The first way to do it, like I just said, this graphical method, is you would lay the vectors out on a graph, tail to nose, tail to nose. And how would you lay them out? Well, you've got a protractor, which measures the angle, and then you have a ruler right here, which measures the length. Okay, so you're probably thinking, well, if you just know the x and y coordinates, that's the calculation way. That's how you would calculate where those vectors are. But if you just want to go outside and walk off some vectors, then you just need to have an angle measuring device and a ruler. And then you go tail to nose, and when you get to your destination, then you run a line from the first tail to the last nose. So you can see up here it says tail to nose, that's how it goes. And that'll give you the polar coordinates. So then you get your protractor out again, you measure that angle. By the way, remember, our angles are measured from North Pole. Okay, so this is 0 degrees right here. See, I got the compass rose right there. So this angle is 53 degrees, and then you measure the length of that thing, and it turns out to be 81.2 meters. Now, the length of this thing is actually not 81.2 meters. You need a huge piece of paper for that, but it's scaled to 81.2 meters. So one of the objectives of this lab is for you to learn how to use a scale on a map to draw the maps, draw your bearings on a map so everything is properly scaled. Okay? So that's how you would do it, using polar coordinates, and you'll be doing that, and then you're going to go ahead and do the calculations. So when you do the calculations, you need to break everything up into x and y coordinates, and it doesn't matter now if you're measuring off the y-axis or you're measuring off the x-axis. So in this particular drawing here, I have the normal angles for doing the math. But you see this angle right here, 36.6, would be 90 minus what that angle was measuring off the north. So when you do your math, you can do it any way you want. But make sure you get the proper x-coordinate and the proper y-coordinate. And then when you go to add those up, all the x-coordinates add up, ax plus bx plus cx plus dx. And all the y-coordinates add up, ay plus by plus cy, and all the way down the line. And then that will give you rx and ry. Those are called the Cartesian coordinates. Those are the x and y coordinates. And then if you want to go back to polar, which you're going to have to do, then you just square the x, rx squared plus ry squared, and then take the square root, and then do an inverse tangent of rx over ry to get the angle. All right, so that's the math for vector addition. All right, let me see what my next slide is. And you can see that. That's going to be for the experimental part. And we're just going to start a brand new video to keep everything separate. So in just a second, we're going to do another video called the experiment. All right, so over and out. We'll see you in 1 second.